Welcome to this explainer. Today, we're popping the hood on a tiny, but honestly, incredibly powerful piece of silicone, the Texas Instruments TCAN1042. Now, if you work in embedded systems, industrial automation, or automotive design, you already know the deal. Microcontrollers need to talk to each other constantly, but the physical environments they operate in, they are chaotic, noisy, and just full of extreme electrical hazards. Well, enter the TCAN1042. You can think of it as the ultimate translator and bouncer for your microcontroller's communications. It makes sure the right messages get through while aggressively keeping the electrical noise and severe voltage spikes out. Today, we're going to completely explain the working of this chip and see exactly how it pulls that off. Let's dive right in by looking at why this chip earns its TurboCAN moniker. It doesn't just check the box for the modern ISO 1189-2016 standards. It really pushes the physical limits of the bus. Obviously, it easily handles classic CAN and your standard 2 megabits per second CAN FD. But if you grab the G suffix option, you can push your data rates all the way up to a blistering 5 megabits per second. Plus, it plays perfectly with both 3.3-volt and 5-volt microcontrollers. Oh, and those H variants? They can withstand up to plus or minus 70 volts of bus fault protection. I mean, that is some serious electrical armor for high-speed data. So, to make this dense technical datasheet a bit more digestible, here is our roadmap for today. First, we'll meet the TCAN1042 transceiver. Then, we'll peek inside the block diagram, cover some clever failsafes like the TXD dominant timeout, look at how it handles undervoltage and faults, and wrap up with the normal and standby modes.
All right, part 1. Meet the TCAN1042 transceiver and its problem-solution architecture. Let's start by understanding the fundamental problem this microchip solves out in the real world.
You know how fragile a typical microcontroller is, right? It operates on low voltages and expects super clean, quiet signals. But a controller area network, or CAN bus, spanning across a piece of heavy machinery, that is the exact opposite. It's a rugged, hostile environment, prone to nasty voltage spikes and severe electromagnetic interference. The TCAN4212 sits right between those two worlds. It acts as a vital bridge. To explain the working here, it translates your delicate single-ended logic signals into robust differential signals. By sending the exact same data as opposing voltages down two separate wires, that differential signaling inherently cancels out electromagnetic noise. And it does all this while surviving junction temperatures from a freezing minus 55 degrees Celsius all the way up to a blistering 150 degrees Celsius.
Moving right along to part 2, inside the block diagram, or a day in the life of a signal.
Let's actually trace the exact path a digital signal takes through the chip to explain its inner workings. You've got your critical pins to keep in mind here. You have the logic side interacting with your microcontroller, specifically the TXD or transmit data pin and the RXD or receive data pin. Then, facing the external bus side, you've got CAN H and CAN L. That's CAN high and CAN low.
So here's how the working actually plays out in 4 simple steps. When your microcontroller wants to talk, the logic signal enters the TXD pin. The chip's internal driver instantly translates that logic into a differential voltage, basically blasting it out onto the CAN H and CAN L bus wires. Conversely, when a message comes down the bus from somewhere else, the chip's internal receiver reads that differential signal, cleanly translates it back into a digital logic format, and feeds it safely right back to the microcontroller through the RXD pin. It's just this elegant, continuous loop of translation.
But, what happens if something goes horribly wrong and holds a transmit pin down constantly? That brings us to part 3, failsafes, specifically the TXD dominant timeout and preventing network jams. This is easily one of the most brilliant failsafes built into the TCAN1042. It's called the TXD dominant timeout, or DTO. Now, to explain the working of a CAN network really quickly, bus arbitration dictates that a dominant 0 state wins out over absolutely everything. So if a broken node gets stuck continuously transmitting a dominant state, it completely overwrites all other traffic. No other machine on that entire network can communicate. It is a catastrophic network jam. But the DTO is a dedicated hardware protection circuit that watches the TXD pin like a hawk. If it's held dominant, meaning a low state, longer than a specific safe timeout period, the chip automatically steps in and physically disables its own CAN driver. To really grasp this, just imagine the timeline of a normal CAN bus. You have rapid alternating highs and lows. But then a fault occurs, a long, stuck dominant signal. Without the DTO, that stuck signal jams the bus completely. Every other sensor, motor, and controller on that line is effectively silenced because one single broken node is shouting endlessly into the void.
But here is the fix. Once that specific timeout window expires, the TCAN1042 just cuts off the babbling driver. Instantly, normal communication from all the other nodes on the network is fully restored. The bus is totally free again. It essentially stops a localized failure from snowballing into a system-wide blackout. Okay, part 4, handling undervoltage and faults and surviving the elements. Let's see how this chip handles power supply drops and massive electrical surges. First up, undervoltage. If the primary power supply, VCC, drops below a specific safe threshold, the chip is actually smart enough to know it can no longer guarantee reliable communication. So what does it do? It immediately pivots from a normal active state into a protected high-impedance state. To explain the working here, by going high impedance, the chip basically acts like an open circuit. It completely unloads itself from the bus, ensuring that its own struggling low-power state doesn't act like an electrical anchor dragging the rest of the healthy network down.
And it's not just logic faults or power drops. This chip is a literal fortress against environmental electrical strikes. We're talking massive electrostatic discharge, or ESD protection, absorbing up to a staggering 16 kilovolts for the human body model. Like we mentioned earlier, the bus lines themselves can shrug off extreme fault voltages up to plus or minus 70 volts on those H variants. And hey, if the internal circuitry gets too hot from extreme external temperatures or a continuous short circuit, a thermal shutdown protection kicks in to save the silicon from literally melting itself.
Finally, part 5, normal and standby modes. Let's zoom back out to the broader network context and look at managing power and activity. This entire state of the transceiver is dictated by just a single logic pin called the STB, or standby terminal. When you pull this pin low, the chip is in normal mode. The driver and receiver are fully enabled, and two-way communication is live. But if your microcontroller decides the system can take a break, it pulls the STB pin high. The chip instantly goes to sleep, disabling the high-power driver to save precious energy, which is absolutely crucial in battery-operated applications.
But here is where the working gets really, really clever. Even while asleep in standby mode with the main driver completely off, a tiny low-power receiver stays awake, silently monitoring the CAN bus. It is specifically listening for an ISO standard wake-up pattern, or WUP. As the datasheet notes, once a valid wake-up pattern hits, that wake request is indicated directly to the microcontroller by dropping the RxD output to a low state. It basically nudges the microcontroller awake, letting it know, hey, valid network activity has resumed, time to get back to work.
We've covered a ton of ground today, tracing the exact signal path and unpacking some truly brilliant fail-safe mechanisms inside the TCAN1042. So I'll leave you with this to consider. When you are out there designing for harsh, unpredictable environments, how will these mechanics, the automatic dominant timeouts, the massive 70-volt fault protection, and those flexible 5 megabit turbo data rates, how are they going to directly elevate the reliability of your next embedded architecture? Thanks for joining me on this explainer, and I really hope this helps you build some incredibly resilient systems.